All right, let's dive in. Today, we're going on an expedition. We're journeying into this tiny, microscopic world that's right at the heart of, well, everything we do. We are going to deconstruct the processor, the silicon brain that powers your phone, your laptop, your entire digital life. I mean, have you ever really stopped to wonder about that? How does a box of metal and plastic go from being, well, just a box, to something that can calculate, create art, and connect you with anyone on the planet? That's the big question we're tackling today. And it all comes down to one tiny, unbelievably powerful little chip. And here it is. Meet the Central Processing Unit, or as you probably know it, the CPU. It is without a doubt the brain of the entire operation. This little guy, about the size of a matchbook, is covered in millions of microscopic circuits. It slots right into the main circuit board, the motherboard, and acts as the command center for the whole system. This is where all the thinking actually happens. Okay, so to really get what a CPU does, we need to go inside. So think of me as your field guide for the next few minutes. We're taking a tour of the processor's core, and we're about to meet the three key players that make all the magic happen.
Here's our map for the tour. Every single thing your computer does, every click, every keystroke, is handled by a team of three components working together perfectly. We've got our calculator, our manager, and our scratch pad. Let's go meet each of them.
So, our first stop is the Arithmetic Logic Unit, or ALU for short. You can just think of it as the calculator. This is the raw mathematical muscle of the processor. Anytime your computer needs to add numbers or compare if one thing is bigger than another, the ALU is what's doing that heavy lifting, and it's doing it at speeds that are just mind-boggling. Next up on our tour, let's meet the control unit. Now this part is super important. It doesn't do any of the math itself. Instead, it's the manager, the traffic controller of the whole operation. It grabs instructions from your software, figures out what they mean, and then tells everyone else, the ALU, the memory, exactly what to do and when to do it. It's the ultimate coordinator. And our final stop inside the core brings us to the scratch pad. These are technically called registers. Just imagine them as tiny little pieces of super fast paper sitting right next to the calculator. They hold the exact numbers the ALU needs for its very next calculation. This means there's absolutely zero delay. And here, speed is everything. So, okay, we've met our team, the calculator, the manager, and the scratch pad. But how do they actually get any work done? Well, they all operate on this constant, four-step rhythm. It's like the very pulse of the machine. This loop is called the instruction cycle, and it happens billions of times, every single second. It's really wild. And it's broken down into two simple phases. First, you've got instruction time, which is all about getting ready. And second, there's execution time, which is when the action happens. Let's break that down.
The pulse always starts with instruction time. Step 1 is fetch. The CPU goes and grabs a new command from the system's memory. You can think of it like a new order ticket coming into the kitchen. Then, step 2 is decode. The control unit, our manager, reads that ticket and figures out exactly what needs to be done.
Then, immediately, it's execution time. In step 3, execute, the ALU, our calculator, gets to work and performs the actual operation. And finally, step 4 is write back. The answer from that calculation gets stored back into memory. Fetch, decode, execute, write back. Over and over. That's the beat that powers our entire digital world. You know, for a long time, the goal was just to make that four-step pulse faster. But eventually, engineers hit a wall and came up with a much smarter idea. What if, instead of one super-fast worker, we had a whole team?
And that, right there, is the magic behind multi-core processors. A single core is like one person trying to do everything. But a dual-core processor, that's two workers sharing the load. A quad-core can handle your game, your chat app, and your web browser all at once. And an octa-core processor becomes a full-on squad, perfect for the really heavy stuff like professional video editing. It's simple. More cores means more work gets done at the same time.
But the CPU isn't the only brain in your computer. No, it has a very specialized partner that handles a totally different kind of thinking. This is the classic story of the generalist versus the specialist.
So, think of the CPU as the general. It's incredibly smart, it's flexible, and it can handle any kind of logical problem you throw at it. The Graphics Processing Unit, or GPU, is the specialist. It's designed to do one thing, and do it perfectly, performing thousands of simple calculations all at the same time. And that's exactly what you need to draw the millions of pixels that make up the images on your screen. The CPU plans the attack, and the GPU executes it flawlessly.
Whew. Okay, that was quite the expedition. Before we head back to base camp, let's just quickly go over the essential checkpoints from our tour. This is the stuff you'll really want to remember.
Okay, let's review. Checkpoint number 1. The CPU is the main coordinator, and it's made of two key parts, the ALU that does all the math, and the control unit that acts as the manager. Checkpoint 2. It runs on that constant 4-step pulse: fetch, decode, execute, and write back. And finally, checkpoint 3. Multi-core processors are all about teamwork. They use a team of workers to boost performance and let you multitask. Got it? Awesome.
So what's next for our silicon brain? Well, the future isn't just about cramming more and more cores onto a chip. It's about making those cores smarter. Your phone probably already does this. It uses powerful cheetah cores for demanding stuff like games, and then switches to low-energy turtle cores for simple background tasks. It proves the goal is shifting from just raw power to real intelligence. The brain isn't just getting bigger, it's getting wiser. Thanks for joining the tour.